Hello, everyone. Today we're going to be continuing our conversation about chemical reactions by focusing in a little bit more tightly on chemical equilibrium. So let's go ahead and start again with our nice simple case of an ideal gas reaction, because it turns out ideal gases are wonderful things to work with. So if I start with the simple case of A goes to B, well, in this case, as we showed last time, the free energy of reaction is simply going to be the difference in chemical potentials of, of our products minus our reactants. However, one of the things that we have to make sure to address is the fact that these chemical potentials aren't referenced to the standard state chemical potentials. They are going to assume a certain change with regard to concentration. So if I'm dealing with an ideal gas, we've already demonstrated that the free energy of a ideal gas is going to change with respect to the pressure of the gas. So we can essentially give the chemical potential of B with regard to the standard state chemical potential of B plus RT, the natural log of the ratio of B to our standard state conditions. And again, we can do the same thing with A. Now, when I do this, what we can do is essentially rearrange our equation to go ahead and collect our standard state chemical potential terms and our pressure terms together. And so when we do this, what we find is that our free energy of reaction can be given as the standard state free energy of reaction plus RT, the natural log of the ratio of products over reactants. And again, with respect to the concentration, here given as pressure. Well, it turns out we can go ahead and extend this idea quite a far way, where we can replace this ratio of products and reactants as the reaction quotient, where again, this is going to be a ratio of products to reactants, again, since this is a gas given in terms of partial pressures of the respective species. However, what we're often interested in is trying to determine the point at which the system reaches equilibrium. What's the most favorable ratio of the products and reactants? Well, it turns out when we do this, well, then the free energy is going to go to zero, because that's going to give us a reversible or equilibrium system. And we give our reaction quotient a special name of K. So at this point, what we can do is provide the standard state free energy of reaction is going to equal to negative RT ln of K, because we essentially just rearrange the equation. This term goes to zero, move the free energy to the other side, generating our negative sign. And this is, in my opinion, one of the more important relationships in chemical thermodynamics, as it gives us essentially a look of where a reaction reaches equilibrium simply with regard to the standard state conditions. And so one of the important things when we look at this essentially free energy ratio is that, as we kind of commented last time, it's mostly going to be driven by the entropy of mixing. Because again, our free energy of mixing for a regular solution is entirely driven by this entropic process, that the system wants to be completely and perfectly mixed. And so we tend to favor this extent of reaction of 0.5, where I have an even mixture of both species. And in truth, if I have we're going to see exactly this relationship if my change in standard state free energy is zero, that the most favorable mixing is going to be this 50-50 mixture. But more or less what ends up happening is the more biased my reaction comes towards one end or another, we're going to tend to favor equilibrium a little bit more in the direction that maximizes. But the introduction of this mixing is always going to drive us a little bit in the other side, because we're always essentially going to be including this feature of wanting to have an extra little bit of mixing on top of the free energy just being based on products minus reactants. We get an extra little boost from this mixing. And that's something that's always important to remember. Because without essentially entropic, I'd expect the free energy from the extent of reaction to simply be X percent of B plus Y percent of A, where it would literally just be the free energies of products minus reactants added together. But instead, we have to realize there's going to be this extra feature based on pressures. And this is really going to what's going to drive our mixing species. And we can also look at this from essentially another perspective, where I can essentially take this relationship in between my standard states and the equilibrium composition of my system. Well, I can go ahead and rearrange this to one of my favorite expressions, where the equilibrium composition can be given as the exponential of essentially the change in free energy of the species. Now, this equational form should hopefully look very familiar to you by this point, because this is a Boltzmann equation. It really shows us the probability of being in a certain state, in this case, the product state, simply as a relationship in between the energy state, how high our energy is with regard to some reference. The lower our energy is, so the more negative, the more I'm going to tend to favor my product species. And again, it's really just a different form of a Boltzmann distribution. However, one of the other important things to make note of is we can split up our free energy contributions into the enthalpic and the entropic parts, where again, enthalpy is going to dictate how good of bonds I'm going to form. So essentially, just how favorable is that state. And then the entropy is going to be a lot more about how many different ways I can form it. And again, all of this dictated by the temperature. So we can then go ahead and use our exponential laws to go ahead and split this term in half. And we're going to end up with an entropy term where the temperature expressions end up annihilating. And when we do this, we can essentially try and evaluate what this more looks like on kind of a statistical distribution. So let's say that I've got this population mixture A, where I have an exothermic endothermic reaction where B is higher in energy than A, and the entropy splittings are fairly equal. So what this tells me is that I'm sitting at a state that is fairly favorable. And I end up with a set of states that is higher in energy. I don't want to be there. And more importantly, the energy splittings are going to be about the same number of states in A as in B for any given energy level. So again, at low temperatures, well, I'm going to tend to populate my low energy species. And it takes fairly high energy or high temperatures before I start occupying B. But something interesting happens when my entropy for B now becomes higher than A. So at this point, what ends up happening is I can tend to favor my product species, because now, while A might be a lot more favorable, I can only say fill 4 states before I can start filling a whole bunch of B states that don't look so bad. So what entropy is going to be telling us a lot, enthalpy tells us a lot about who I can fill, who we imagine as being more favorable. If essentially I can only arrange, I can only produce so many favorable molecules of A, but I can produce a lot of favorable molecules of B. If my temperature reaches any substantial portion, I'm going to tend to favor the entropy favored product. And this is what we're often talking about with the balance of entropy and enthalpy. And again, this is really what we're kind of seeing with these Boltzmann sort of distributions. Enthalpy is going to tell me a lot about essentially the ground states, but unless I'm dealing with very low temperature systems, I'm going to tend to favor a certain amount of B. And the And the lower in energy B is, and the more states it has, the more likely I am to increasingly populate B. And this is really what K is telling us, is it's going to be telling me a ratio of, for every state of A I occupy, how many states of B can I occupy at, again, this same temperature. And this is one of the reasons why we do see such temperature dependence of our equilibrium constants. Now, one of the other things that's worth noting is that we just looked at a simple relationship of A goes to B. In truth, we often have a lot more complicated reactions. So we want to go ahead and extend our free energies and thus our equilibrium constants to include, making any number of chemical species. And in this case, what I can do is um, provide the total free energy of the system with regard to the sum of any number of chemical constituents that may be present, either as products or as reactants. And simply that the total free energy of the system will be given as the chemical potential of each of these chemical components times how much of a change I'm seeing in each of these chemical components. However, again, this gives us a lot of different variables. So again, we conveniently want to describe all of our change with regard to our extent of reaction. And as we showed last time, we can essentially make the relationship in between the number of moles of J by its stoichiometric coefficient. And again, this is quite a translatable portion, whether I'm dealing with 1, 2, or 20 chemical species, giving us a lot of power. And in this case, again, I can then evaluate the free energy of reaction as the change in this free energy with regard to extent of reaction, again, under constant pressure and temperature. And because of this constant pressure and temperature, the only contributor to the free energy that's left is going to be more or less the sum of our chemical potentials and the stoichiometric coefficients, which again, we can then split up into the standard state chemical potential. And now, instead of it being a pressure, because we want something that's more kind of universal, we're going to make use of activity, because activity can represent a condensed phase, an aqueous species, or a gas phase species. And so what we can then do is we'll note that the sum of all of these standard state chemical potentials is just going to be our standard state free energy. However, over here, we've got the sum of a coefficient times a natural log. Well, it turns out that this is going to be the same thing as the natural log of those same activities raised to the power of their coefficients. So what we can then do is take this big, messy product of activities, and now we're going to refer to this as our more generalized reaction quotient. And again, just like for a binary system, what I can do is I can set the free energy of reaction equal to 0 to define an equilibrium system. And again, whether I've got 2 or 20 components, Q is always going to equal K. And in this case, we find that we can then make a more general relationship in between the standard state free energy and our equilibrium constant. So again, as long as I'm able to go ahead and look up my standard state chemical potentials in a nice table, say your CRC or an online resource, you can use those to determine the reaction quotient for any number of chemical reactions. And again, to give us our equilibrium constants that we so deeply treasure. Now, in this case, we do have to worry a little bit more about what the form our K is going to take. And again, the most general good expression for the K is it's going to be the product of all of our chemical activities to their stoichiometric coefficients. Now, one of the things to make note of is that how we express activities does change with the nature of the species we're examining. So for example, for gases, I can split up my activities into my activity coefficients, again, our fugacity coefficients, and our partial pressures of each species, still raised to the to the stoichiometric coefficient. And so in this case, we can express our K as K gamma. So this is essentially our kind of fudge factor equilibrium constant, and our K just in terms of the partial pressures. So many times this is the K that we tend to make use of, and we tend to try and hope that we can ignore the activity coefficients. But again, this lets us evaluate our system if, say, I'm able to measure my ratio of partial pressures, and then I might be able to look up my fugacity coefficients and add in a correction factor to get to the true K, which will again be related to our true free energy potential. And we can make a similar relationship for solutes, where again, this time our activity is going to be related to our activity coefficient times either our mole fraction, which is a little inconvenient, or if I have a true solute system, I can relate it to the molarities of each of the individual components. It's worth noting here, we've divided each of our molarities by the standard state molality of, again, 1 molal, just to avoid any kind of confusion with the units. And again, all of this is going to be raised to the power of our stoichiometric coefficients. Now, one of the things I want to make note of is is that in order to truly reflect the equilibrium constants, we should be making use of molality, not molarity. However, for many truly dilute systems, we often approximate this as 1 molal being equivalent to 1 molar. While not technically true, it will get you in the rough ballpark. However, if you're wanting to do very accurate calculations, you should make sure to make use of molality to truly represent the system. However, as a consequence, most people instead will make use of a Kc, which is essentially our equilibrium constant, which truly reflects our molarity, again, corrected for a standard state of 1 molar instead of our more traditional molality. Now, one of the other things that I want to make note of is that we can use any of these forms to essentially truly model a system with a mixed phase. So you can imagine a system like Henry's, where I have a solute which can then evaporate to form a gas. And in this case, you can use your activities to include both pressures and molalities. And again, you can even use this to include condensed phases, which we're kind of inherently doing with solutes, because what we should always make sure to include is the solvent. But in this case, we can also make use of the fact that our activity is going to be 1 for either solids or pure liquids. So in that case, they'll essentially, we'll be able to neglect these for a equilibrium system, because when I multiply by 1, no matter what the stoichiometric coefficient is, I'm always going to get my same value back. So this is one of the reasons why we traditionally ignore solids or pure liquids. But again, they can be included in this notation. Now, one of the other things that a lot of people tend to do is they often try and prefer to represent gas equilibrium. They want to relate their equilibrium constant for an ideal gas to the Kc. They want to essentially be able to express their equilibrium constant in terms of molarity. And in order to do this, we're going to need to make use of some ideal gas relationships, which again, we can actually do fairly accurately, because any non-ideality should be accounted for in the K gamma, so we can evaluate the ideal component on its own. And when we do this, we can, again, start with the simple idea of an ideal gas. So the pressure of the individual component can be given in terms of the moles of the individual component times RT over, again, the total volume, which should be invariant no matter what component you're looking at, and should be a shared variable. Now, in this case, what we can then do is make use of the fact that moles over volume is going to be the same thing as molarity, at which point I can go ahead and pull out the molarity term, again, still raised to the stoichiometric coefficient, and multiply it by our constant values, R T being considered constant because, again, one of the assumptions of our free energy of reaction is isothermal. So in this case, we're going to assume the temperature does not change. And again, our standard state conditions, which by definition are standard state. Now, one of the issues with working with this is that we do end up with a little bit of messiness of units, as we have units on this component and units on this component, where again, this will be given as moles to the power of the coefficient, and this side will be inverse moles, inverse molarity, again, coming from the R to the power of the coefficient. So we can correct for this term by simply dividing this term by a standard state concentration, again, 1 molar, and multiplying this side by 1 molar. And again, this will be equivalent to multiplying the whole thing by C naught over C naught, because again, we have similar, identical stoichiometric coefficients, so those cancel out. And when we do this, you may notice that the first term is going to be our equilibrium constant in terms of concentration, and now we essentially have a simple correction factor as a subsequent term, where again, we can then now relate the equilibrium constant with respect to pressures to the equilibrium constant with respect to concentrations with a correction factor that's dependent on the change in the stoichiometric coefficients. So let's go ahead and look specifically at an example to explain what I'm doing. So let's look at the example of the decomposition of dinitrogen tetroxide. And this can decompose to at high temps to form nitrogen oxide. So at this point, we're going to have an increase in our stoichiometric coefficient by 1. So our equilibrium constant is going to be equal to our concentration equilibrium constant times, again, our coefficients correcting for units, RT, times, again, an increase of the coefficients of 1, so just simply KCRT. And again, it is worth noting that this does make an assumption that we're dealing exclusively with ideal gases. But you can also, if you have a mixed system, use this to turn any pressures into concentrations, as long as you realize that the change in coefficients you're looking at is just the change in coefficients in the gas phase. So this essentially gives us a quick rundown of how we get to the equilibrium constants that you've used so much in other classes. So next time, we're going to focus a little bit more on how these equilibrium constants will change under external perturbations, specifically pressure and temperature. Until then, take care.